Hello and welcome to your last week before break. We got a nice short week coming through here. Really small problem sets. So hopefully it will go nice and smooth. If you have any questions on anything from quarter 3, please let me know and I'm happy to talk to you about anything regarding content or grades or anything like that. So get yourself ready for notes and we're going to get started. We're going to start talking about equivalence classes and also this new idea called partitions. So the first thing that we're going to want to do is define partition. Now we would say that a partition on a set A or of a set A is a set of subsets of A such that, and this is the important idea, is that the union of all the subsets equals A. So what that means is that there's no one left out, right? Every single element is in one of the subsets, and the intersection of any two subsets is the null set. So the idea here is that no element is in multiple subsets and every single element is in one of the subsets. So let's look at a couple examples. So list all the partitions of A. So what this means is that we can make subsets. So one partition of A would be like A, and then B and C. So what we can see here is that we have A, B, and C. We have all the elements, but there's no overlap. There's no intersection. You could have A and B together, and then C. You could have A and C together with B. You can also just have it as A, B, and C. This is a partition made up of just A. You can also have it where they're all separate and C. So these are the possible partitions here of the set A. Now, recall from problem number 3, which we looked at in our last week. From 11.3 notes, the relation equivalent in mod 3 is an equivalence relation. Describe the partition created by that. So the partition was ... We had -3, 0, 3, and so on. We then had another set of -2, 1, 4, and our third set was -1, 2, 5, etc. And so what you'll notice here is that these are also the equivalence classes 3 or 0, I think is how we wrote it in the notes. The equivalence class of 1 and the equivalence class of 2. And so this idea is what we're going to look at in number 3. If R is an equivalence relation on set A, prove that the set of equivalence classes, so in our example 0, 1, and 2, but here just any, forms a partition. So whenever we want to show that something forms a partition, our goal is that we want to show that for all A in A, that A is in some subset. Sorry if you hear thunder, it's raining outside today. So that's the idea that no element's left out. And we want to show that if the two classes are not equal. So what we want to show is that if these aren't equal, then the intersection that they have is the null set. Because as we talked about last week, sometimes the equivalence class of A is equal to the equivalence class of B, but then they're completely equal, just like the equivalence class 0 would be completely equal to the equivalence class of 3. So the first one is going to be very straightforward to prove. So suppose that X is some element of A, since R is an equivalence relation, we know that XRX is in the relation. Hence, and this is something we've touched on with previous notes, is that X, I'm going to write that slightly different. And what that means is that X is always going to be in the equivalence class of itself. Right? And so what we know is, using the reflexive property, then therefore for all X in A, X is in the set of the equivalence classes. Right? Because it's reflexive, we know that every part is in there. So that's this first part here. The second one's a little bit trickier, because we want to show that a set is empty. So what I'm going to actually use here is, because it's really hard to prove a negative, I'm going to use a proof by the contrapositive. So I'm going to say, so remember, our goal is that if A and B are not equal, then A intersect B is equal to the null set. So in this case, I'm going to use the contrapositive. And what that says is that if the intersection is not equal to the null set, then A is equal to B. So I'm going to suppose that the intersection of A and B is not the null set, and what that means is that it contains at least one element. That's what it means to not be a null set. Therefore, I'm going to say that X is in A and X is in B for some X in A. Right? That's what it means to be in the intersection. Therefore, what we know is, because it's an equivalence class, that means that X R A, which this by the symmetric property, that means that X, right? By the fact that R is an equivalence class, so it's symmetric, and this is as equally true here. So then, by the transitive property of the equivalence class, if we look here, we know that A are X and X are B. We can say that A, B. Okay, using a theorem that you hopefully maybe have used in some of your work up till now, if you look in the textbook, Theorem 11.1 proves that if A are B, then the two equivalence classes are the same. So basically, and this is something that's been really helpful in some of your proofs if you've used it, and I've talked to some of you about it, is the idea is that if an element has an overlap in an equivalence class, then they are in the same equivalence class, and their equivalence classes are equal. So we have proven the contrapositive. So by proof of the contrapositive the set of equivalence classes in a equivalence relation, oh, not R, but that should be the set A, forms a partition. If you have questions about any of this vocabulary, please reach out, let me know, and I will be happy to work with you through all these problems.